This video is looking at free radical substitution reactions. So first of all, we need to understand what a radical is in order to know how it reacts. So a radical is formed by homolytic fission. If you can't quite remember what homolytic fission is, you need to go back and look at the different video about types of mechanism. Basically though, homolytic fission is where one electron will move to one side of the bond and the other electron in the bond will move to the other's atom. Some bonds are weak enough to undergo fission spontaneously, so that means they don't really need any extra energy from UV light. However, most times that you come across homolytic fission, it's in the presence of UV light, and that's the energy from that light that is going to break the bonds. Again, it's only some bonds that will do this. Most bonds will not break under UV light. They have to be fairly weak bonds. The example of free radical substitution that you do at AS level most detail is the reaction of methane and chlorine. Some other examples though will be reactions that occur in the ozone layer and also polymerization. So addition polymerization is also a free radical reaction. In a reaction of methane and chlorine then, one of the hydrogens in the methane molecule is replaced by a chlorine atom and you get hydrogen chloride, HCl, as a byproduct. This is only one example of one of the types of the reactions, the overall main reaction that occurs. There will be side reactions which we'll cover, and the reason there are side reactions is because the reaction doesn't all happen in one step. Like all free radical reactions, it happens in 3 steps. Those are initiation, propagation, and termination. So we're going to look at each of these stages in kind of more detail. It's important to know that because there are 3 stages doesn't mean there are only going to be 3 chemical equations to write. Looking at initiation. In initiation, you're going to need to use some energy from UV light to break a bond. At the start of the reaction, you've got 2 substances present only. You've got methane in large quantities and you've got chlorine in large quantities. And we're going to assume that there's some UV light coming from somewhere. So there's a choice of either breaking a CH bond or breaking a Cl-Cl bond. Now, the CH bond is pretty strong compared to the chlorine-chlorine bond. That's why alkanes are fairly unreactive. So, it's the chlorine-chlorine bond that undergoes homolytic fission to produce radicals. UV light is absorbed by the electrons in the bond. This excites them to higher energy levels and the whole bond becomes unstable. At this point, because there is no dipole in the bond, there's no reason for either electron to move in one particular direction. So that means that one electron goes to one chlorine atom and the other electron goes to the other chlorine atom. The bond breaks and you get 2 chlorine radicals, which are essentially just chlorine atoms. They have 7 electrons in the outer shell, which means that one of the electrons is unpaired, and that is what makes this an extremely reactive species. Now, remember, only a few of the chlorine molecules at the start are going to be broken up like this. Some of these chlorine radicals might collide with a chlorine molecule, but if they do that, all that's going to happen is that they take an electron away and you end up with exactly what you started with. So the only way you're going to get a reaction occurring is when a chlorine radical actually collides with a methane molecule, because those are the only other things present at the start of the reaction. So here are my chlorine molecules. They're splitting up into 2 Cl radicals. So I'm starting with a non-radical, ending up with 2 radicals. And that is the kind of definition of my initiation step. That's what happens when you go from something that isn't a radical to something that is a radical, usually in the presence of UV. So the chlorine radical, as we said, is going to collide with a methane molecule. And it's going to form a bond with the first atom it becomes close to. Radicals are very reactive. They're not attracted to anything in particular. All they want to do is pair that electron up. So the first atom that you come into contact with on a methane molecule is a hydrogen atom. When it does this, we're using the single-headed arrows to show what happens to the electrons. One electron from the chlorine is going to pair with one electron from the hydrogen. That means that the carbon is left with one unpaired electron, because previously there were two electrons, one from the carbon and one from the hydrogen. So the chlorine atom has now formed a stable molecule, HCl. That's the thing we saw as a byproduct in the reaction. It's actually the first thing that forms. But the methane has become what's known as a methyl radical. It's a CH3, so it's methyl, not methane, and it's got that one unpaired electron. No charge, because it's got no overall additional or fewer electrons than it started with. If we were going to write that as a balanced equation, it would look like this. A chlorine radical plus CH4 makes HCl plus CH3. That is a propagation step. It's a propagation step because although you're using up the chlorine radical, you're making another radical in the process. So you're allowing the reaction to continue because you've made another radical. The CH3 radical now has to go and react with something else. The CH3 radical could go and collide with a methane molecule because there are lots of methane molecules present, but if it did that, all it would do would take an H off and leave another CH3, so there would be no reaction happening from that. So at the start, the methyl radical is most likely to combine with something that's not a radical at the moment, because we're talking the early stages of the reaction. Only a few of those chlorine molecules have been broken up by UV light, and some of them have got back together and formed chlorine again. So it's much more likely at this stage that the CH3 radical is going to combine with the kind of undissociated chlorine molecules than if it would combine with a chlorine radical, because there aren't many chlorine radicals around. When it does this, one electron from the methyl radical is going to combine with an electron from one of the chlorine atoms to form a new bond, and the other chlorine will end up with just a single unpaired electron again, with an unpaired electron like so. So we have made our final products. We have made chloromethane and a chlorine radical. The chlorine radical can continue the reaction though, so we've remade the chlorine radical, which can now go and react with methane. So this is still a propagation step because we haven't used up the radicals. We've used up the methyl radical, but we've created a chlorine radical, and so therefore we're allowing the reaction to continue. So notice there were two propagation steps, not just one. So after a while, when this reaction is just continuing, there's going to be a higher and higher concentration of radicals building up. As these radicals keep colliding and pulling electrons of each other, eventually you're going to get to a point where there are more radicals in the mixture than non-radicals. So by this point it becomes increasingly likely that two radicals will collide. And when this, they'll bring their unpaired electrons and they will make a non-radical molecule. So this is what it looks like as an equation. In this case, it's the methyl radical coming together with the chlorine radical, again to make our product, the organic product, chloromethane. That's a termination step. The carbon-chlorine bond is much stronger than the chlorine-chlorine bond. It's not going to break under UV light. The carbon-hydrogen bond is strong as well, and that won't break. So we've reached a stable molecule that isn't going to break down under UV. We have got no radicals on the right hand side in our products, so the reaction is essentially finished. That's not the only possible termination step though. Remember we said that these three stages can have more than one balanced equation, because there's no reason why, when you've got a high concentration of methyl radicals floating around, that they couldn't combine as well. Remember, radicals have no preference, they are just going to pair that electron up. So if methyl radicals come together, you will form ethane. One of the byproducts in the reaction, therefore, will be that you will get some ethane as well as chloromethane. This is still a termination step, because you've still taken two radicals, you formed a strong carbon-carbon bond, which has therefore ended the reaction, can go no further. Now, some books will show you that two chlorine radicals could also come together, and they will give this as an example of a termination step. It's not the best example of a termination step because the chlorine-chlorine bond is weak and could break under UV light, and so the reaction could start again, assuming that it was still being irradiated by UV. So the overall reaction, as we saw at the beginning, is our methane plus our chlorine. It's a substitution, so we're swapping in one of the chlorine atoms for one of the hydrogen atoms in methane. The product is called chloromethane. We don't need a number on it, because methane only has one carbon. It's known as a monosubstituted product because only one of the hydrogens has been substituted for chlorine. So what happens if that chloromethane, once it's produced, comes into contact with a chlorine radical? So for example, chloromethane may have been produced near the start of the reaction and there are still some chlorine radicals being made. Well, the chlorine radical is going to do exactly what the chlorine radical did in the propagation step before, and it will remove a hydrogen from the chloromethane. That chloromethane or chloromethyl radical can then come into contact with another chlorine molecule. See, what's happening now is that we've actually now substituted two of the hydrogens on the methane for chlorine atom. There's our overall equation for that step, and there's the overall equation for what's happening. You've got two overall reactions. Methane's reacting with chlorine to make chloromethane and hydrogen chloride. That chloromethane can then further react in exactly the same way, in the same steps, with another chlorine molecule to substitute another hydrogen atom. This time, we've made dichloromethane. That's a di-substituted product. But notice we've made another HCl, so we haven't just swapped two hydrogen atoms for two chlorines and not left anything over. So therefore, if I wanted to do a full balanced equation to show the production of dichloromethane, I would need to use two chlorine molecules, substitute two of the hydrogens and produce two molecules of HCl. Similarly, if I wanted a tetra-substituted product, if I wanted to make tetrachloromethane, then I would add 4 chlorine molecules and I would produce 4 lots of HCl. And it's all just going to become part of the product. So you're going to have a mixture of mostly chloromethane, and that's mostly chloromethane simply because statistically that's the most likely thing that will form. You're going to get some ethane, and then you're going to get some di and tri and tetra substituted methane molecules as well. That's everything you need to know about free radical substitution. Now you should have a look at the videos on electrophilic addition and nucleophilic substitution.